Hello. In this tutorial, we are going to learn to model flow around a wind turbine. Here we have a wind turbine, a lab scale wind turbine, and we are going to model that using CFD and Ansys Fluent. For a wind turbine here, we have a power generated from wind. When the wind is passing through this wind tunnel, it's going to generate some power inside the rotor. The power of the rotor is torque times the rotational speed. Torque is represented by T, and rotational speed of the blade of the rotors is going to be represented by omega. And the power of the wind is something like this. Half of rho A V to the power of 3. Rho is density of air, A is the area of the rotor, surface area of the rotor, and V is the speed of the wind coming through the tunnel. So that is kind of the efficiency of the wind turbine. I mean, how much of the wind power is going to be converted to the mechanical power by wind turbine. To model that, we can take a look at here. So for this problem, we have a speed of air or wind speed, 7 meters per second, and the rotational speed is going to be something around 2000 RPM, 1999 RPM. And we are going to calculate the torque as a result of this, basically wind passing through this wind turbine. Once we have torque, we can replace that here because we have the rotational speed, we have the speed of wind, and A is the area covered by the rotor, and rho is density of air. From experimental data, we have the torque 23.5 millinewton meter, and the COP is 0.316, which means that almost 30% of the power from the wind is converted to mechanical power. We are going to use MRF approach. You might ask what MRF is. MRF is multi-reference frame. Why we are going to use that? We have a blade rotating, we have a rotor rotating. So these are rotating valves. If we want to have these valves rotating, we need to rotate the mesh. We need to basically have a moving mesh because of the moving valves. In order to avoid that, we assume the rotor is fixed and the region around the rotor is going to rotate. That is called rotating frame. So rotating frame means the region is going to rotate. That's the rotor, that's the region next to the rotor. We have another region which is going to be a fixed region elsewhere. That's why we have multi-reference frame. So one reference frame is fixed, which is for the region around, the inner cylinder. And the other region which is rotating is the inner cylinder, which is around the rotor. In order to apply that in Fluent, we are going to use Workbench. We use fluid flow here, drag and drop it here, then we need a space claim. We have the geometry, but the geometry is not exactly the geometry from the lab scale wind turbine. That's why the data might be slightly different from the experimental data. But for the purpose of demonstration, we are going to use that geometry. Let's open the geometry. Okay, that is the geometry. We need to create the region around this, the inner region, and then the outer region. First of all, let's simplify the geometry. I would remove this part. So these are basically just the connectors because they are not going to affect the flow around the wind turbine, and by that I will simplify the geometry without reducing the accuracy that much. So I need to create a cylinder around these four components. To do that, I right click here, create new component, and I call it inner enclosure. To create the flow, to create the region around these components, I can use prepare, then enclosure. We can use box, cylinder, sphere, but I'm going to use custom shape. For custom shape, you need to have some geometry prepared, created beforehand. So that's why I need to create a cylinder before using enclosure. In order to create the cylinder, I created the inner enclosure. So the inner enclosure is going to be cylinder around these components. I'm going to draw the cylinder. The best place to start is going to be from here. So select cylinder. I will create the cylinder around this. The size of that I would like to be 600 millimeter because I know the size of the rotor. And then I will pull it backward 100 millimeter and forward 150. So that's the cylinder around the components. I can see it from here. I can hide this face as well. I can see this one. That's the distance. Okay. Let's show all of the faces. Now I can see all of the faces. Let's just hide this face. In order to tell the software this cylinder is going to be region around this component, basically I need to subtract this component from the cylinder. That's what enclosure means. So I can click on prepare, then enclosure, then I can select these components, 4 components, and then I tell the software it's going to be a custom shape because I have created the shape before. Then I go to this basically object, I select this object, then I can select the outer cylinder to tell the outer cylinder is going to be the enclosure. Then press this one. Now I have created the outer cylinder as a region around this rotor. How to make sure? Just you can hide the other regions and the only enclosure is basically selected, and I can see the enclosure is the cylinder minus those components. I can drag it out and put it here, and I can also rename it. Let's call it rotating region flow. I don't need the other regions anymore, so I can just suppress them. So they are all suppressed. That sign means they are suppressed. They are not going to be modeled in the physics. Okay, then I need to create the outer region, the outer cylinder around the inner cylinder. To do so, I can create new components. Let's call it outer cylinder. And I can start from here. So the outer cylinder, let's quit the enclosure command first. Then I select this face as the starting point. Then draw my cylinder around this inner cylinder. The size I'm going to use 1000 millimeter. And then I can pull it backward 2000. Basically, I prefer to be as far as possible. And then this side 1000. Okay, I have created the outer cylinder. Let's hide the face, front face, to be able to see the inner. Then one thing I need to tell the software is we are going to use shared topology. That means the interface between these two components are going to be shared. We will tell the software later, but we can tell it now. If you select this one, you can make sure this is shared topology. That means the interface between the cylinder is going to be shared. Okay, the next step is to tell the software this outer cylinder is the flow around the inner cylinder. Or in another way, we can tell we should subtract the inner cylinder from the outer cylinder. To do so, I can use again prepare, enclosure, and custom shape. Then I select the inner cylinder around which I want to create the enclosure. Then select this object, then select this outer region to tell this is going to be the enclosure. Great. So if I remove the tick, if I hide the inner cylinder and only see the outer cylinder, the enclosure, I can see the enclosure is the outer cylinder minus inner cylinder. That is what I wanted. Perfect. So let's drag it out here again and rename it fix region flow. This one, I don't need that, so I suppress that. All of the geometries are suppressed except these two. Rotating region, which is the inner cylinder minus the blades. So that's how the blade incorporate into my simulation. Outer region or fixed region, which is the outer cylinder minus the inner cylinder. Great. Then I need to define my boundary condition. So this face is going to be the inlet. This face is going to be the outer wall or tunnel walls. Let's call it outer wall. This face is going to be the outflow or outlet. Then for the blades, I need to hide these faces and this face. I can hide all of the faces to make sure I only see the great. So for the blades, they are not perfect blades basically in the CAD model. So you can see there is something like a geometry, the face here. I need to select all of the faces related to the blades. So each blade has 3 faces for me here. One face, second face, and third face. So let's select all of them. Hold Control, first, second, and zoom in, third. Go to the next blade while holding Control, first, second, third. Third. Create an S, let's call it blades, all of them. I can create something else called this nose, for example, and the other faces. But if I don't do that, Fluent will automatically create walls for all of them. And because I know they are walls again, so perhaps I don't have to define them here. Fluent will automatically define all of the other things as face, and the other things, I mean this face and these faces, so many faces here. So I don't define them here. Now let's go to mesh. Double click on mesh. For the mesh, the first thing I will do is to make sure the geometry is all imported. The name selection are there. Then I can create the mesh. To create the mesh, I can use different strategies. I am going to use the simplest one. So first, let's hide this one basically. I want to set a size for this body. So right click, insert sizing. Here, volume selection activated. Select this volume. I want to say this is going to be 0.5 millimeter. I can also, let's hide this face as well. Select face. Hide face because I want to see this, and hide the back face as well. I can set the size for all of these internal things. For example, here, mesh, sizing, and faces, and I can mode for the mode. I can box select. I can select all of the faces here, and I can tell the software the size of that should be 2 millimeter. Then I can tell the software the size elsewhere should be, for example, 1 centimeter. That means the size for the outer body. I can show the outer body. Then let's generate the mesh. We can use different approaches to generate mesh, but that's one simple way to generate a mesh. If you double click here, you can see the stage of mesh generation. This is going to take a while, sometimes a few minutes. Great, I have the mesh generated. This green tick shows that the mesh generated successfully. Let's see. Sometimes you have to make sure that your memory is enough to handle that. So I need to check my memory. Great, so the number of cells are too much because this is a very fine mesh. So 10 million, I can see 10 million elements. So that is very fine. I would use, so 1 centimeter, I can use 5 centimeter. And for this body, I can use 1 centimeter. Because that was very fine mesh. I mean, 10 million elements is you need much more memory to handle that. My computer can handle that, but sometimes it would be problematic to model it. That's why you need to check the number of elements all the time. Okay, now this is a better mesh. If I click on this, I can see number of cells and elements are 1,700,000. Still a large number, but I can manage that. I can still make this, I mean, a better mesh, a finer mesh, or a coarser mesh by playing with this. Okay, for now, this mesh is enough. Let's take a look at the quality of the mesh. If I click on mesh, then click on quality, this is a very important step, then select orthogonality. Make sure the orthogonality here is above 0.2. That's a number that I usually use. The larger number, the better. These are good cells. If I double click on that, I can visualize these cells. Or I can visualize these cells. I can visualize these cells. I can see their numbers. And the worst case is here. If I bring this up, this one, which is still okay, above 0.2. If I double click on them, I can see they are 433, 433, and they are located here. So these are the bad cells, but it's still okay for me. The worst cells are here, these cells, which is still okay for me. Okay, so I have generated the mesh. I'm happy with the quality because 0.2, all of them are above 0.2, which is okay for me. Then if this is below 0.1, I would say that would be a bad mesh. But 0.2 is okay. Even 433 cells are above that point. So I mean, you can see that. And most of the cells are good cells. Then I can right click update, then go to setup. Here, because I have more than 1 million, I have 1,700,000 cells, I would use, for example, 5 cores to make the simulation faster. In order to understand how many cores do you have on your computer, you can right click here, Task Manager and Performance, then click CPU. You can see I have 32 cores and 64 logical processors. I would use the physical cores, 32. I can use that number of cores, but for you it might be less. So for example, if I have 32, I would use, let's say, 25 cores. For you, if you have 10 cores, I would suggest using 8 cores. And start. The more cores you use, the faster the simulation could be. So we have 1,700,000 elements or cells, which is a moderate case for solving, and that might take an hour to solve depending on your computer. Okay, I have the geometry. Before everything, let's make sure we have everything here. So click on General, Display, and come here, and I select blades. Let's make sure I have the blades. I can zoom in. I can click on Edge to see the mesh on the blades. So you can see the mesh is pretty fine, which is good. And I can see inlet, outlet. This interior is the fluid itself, the region. There is something called Wall FF rotating region flow. I didn't create that. This is created by Fluent. If I click on that to see where they are located, I can see the other geometries, nodes and connectors that I didn't define them are all defined as this new boundary condition. I can see the outlet and inlet if I want. If I zoom out, I see the outlet and inlet, and I can see the outer region as well. Okay, so everything is defined as I expected. Then I need to come to model, make sure viscous. So because we are solving turbulent flow, a K omega SST is the best option for this problem. I will go with that. And the material is air. I have air, so that's fine. For cell zone conditions, I have two regions. One is fixed region, one is rotating region. Double click on rotating region. So we are going to use rotating frame. That's why here we need to activate this frame motion. For frame motion, you need to tell the software what is the center of rotation and the axis of rotation. Center of rotation and axis of rotation. What does it mean? So center of rotation is this center, exactly this center of this cylinder. I can find it out here. How to find it out? If I come here and click on measure, and for example, mass properties, if I select, let's say, only this part, let's go to the structure and activate only the nodes. If I select this and mass measurements, it gives me the center of the volume, and I know 0, 21, 0. The only important thing for me is, so if I look at this perspective, Y perspective, the only important factors are X and Z. Y is not important for me because Y is just is the direction of the rotation, and X and Z are important for me, and they are both 0 and 0. So the point for the rotation is this 0 and 0 and 0. This one is not important, as I said, because it's just axis of rotation. And the axis of rotation is basically Y. I can see it here. Y is axis of rotation. So I can set here, if I go to Fluent, I can set 0, 0, 0, and the axis of rotation is going to be Y. And the speed of rotation is going to be 2000 RPM. I have to convert that to radian per second, which is 209 radian per second. I have to convert that to this. 2000 multiplied pi divided by 60. Then what else do I need to know? I need to know the rotation. So if I see the blades here, the blades are telling me the rotation should be always toward the thicker side. So from this side to this side. That's why the rotational axis, if I use my finger, I can understand the rotational axis is negative y. So is it negative y or positive y based on that? Because the thicker side, the leading edge, we call this a leading edge and we call this side trailing edge. So the leading edge is going to be this side and the axis of rotation is based on this. If I click on y, if I use my fingers, I can understand this is negative y. So here, this rotation from here to here would be negative y. That's why I need to say this is negative y or negative. That's the axis of rotation and the rotation direction. And that's the speed of rotation. Apply. For the fixed region, I don't need to define that. This is not going to be rotating. For the boundary condition, I can go to the inlet and the speed is going to be 7. That's the wind speed. For the outlet and other things, I don't have to do anything. If I like, I can tell the software these valves around the wind turbine are going to be no slip or slip valves. How to do that? For example, if I go to valves, I can tell the outer valve to be specified shear stress and it would be 0. So that tells me this outer valve is going to be basically slip valves. So the velocity on them wouldn't be 0. But I can keep them as a tunnel valves. So we have no slip. But for actual wind turbine, basically these are slip valves because we don't have any valves. Then something else that I need to check, I can monitor basically some quantities that I'm interested in. So if I click on monitor and then report plots, click on new and then new here, then force, then moment. What I can do here, I can select moment and blades and I can monitor the moment on the blade while the problem is being solved. The moment center is 0, 0, 0. I know that from the problem. And for this rotational axis or momentum axis should be rotational axis, which is -1. And I can print it to the console. Print it here. I like to use some naming, which is moment or torque, let's call it. That's the torque that we need. You can call it torque as well here. Then click OK. Then click OK. So you can see 2 items are created here. Then I can initialize my simulation. My computer might be faster than yours because the CPU here is more powerful. Then run. So as I said, for number of iterations, just keep it as large as possible. Then in the middle of that, we can stop it. So if I run calculate here, then you have to wait. Sometimes it might take hours depending on the simulation time that you need. So basically this is mesh, this tab is showing mesh, this tab is showing residual. I expect them to come to below 10 to -3. And this is the torque that I'm going to monitor during the simulation. So the torque is changing. Once the torque becomes fixed, doesn't change with iteration anymore, I can assume my simulation has converged and I can stop it from here. This button I can use to stop. It might take, depending on the problem and the quality of the mesh, it might take a few hundred iterations. So you have to be patient, sometimes an hour, sometimes half an hour. For the purpose of this tutorial, you can reduce the size of the mesh and do the simulation. So I can see here that's the torque, and here torque Newton meter. I need to compare this data with this here. Peak torque is 23.5 millinewton meter. So basically 0.0235 or 23.5 times 10 to minus 3. If I look at here, it's changing, and now it's changing, and I can just monitor that through here or through this data report 1def. I should have used a better name. I could use a better name in the first place, and I can see it here, report def. So basically this is the torque, and when it becomes fixed, that's when my simulation converged properly. We can also take a look at residuals, so they should become 10 to minus 3, below 10 to minus 3. Sometimes it might take time, I would say an hour, or if not a few hours. So basically the first one is continuity. This one, the color is y velocity momentum in y direction. This green one is omega. What omega is, because we are solving turbulence K omega SST, so we have K and omega. These are two additional equations being solved because we are using K omega SST. In laminar, we don't have these equations, but we have these equations for turbulent flow K omega SST. For all of them, they should become less than 10 to minus 3. Sometimes they don't become below that threshold. Alternatively, I can take a look at this. When it becomes fixed, with loss of iteration, it is still fixed. I can assume my simulation converged, but I cannot make sure. And if both of them, if this becomes less than 10 to minus 3 and this becomes fixed, it becomes basically horizontal line. That's when I can say my simulation converged. So I'm going to pause the video here, and after perhaps takes 10 minutes, then show you the results. You might wait for that in the lab, or I suggest using a coarser mesh to get faster results. Okay, so now I'm going to stop the project by pressing this button because it's already converged. In a practical project, I wouldn't stop it. I will leave it be horizontal, and I take a look at this number, the last one, which is associated with this curve, and I need to make sure it is fixed during iterations. But it's not completely fixed, it's still changing, it's reducing more and more and more. So I can wait more, perhaps a few hundred iterations. So this is 600. If I wait to 1000, I would see it becomes a straight, horizontal line. And here the numbers are all the same, they are not changing anymore. So the solution is about to converge, it has not converged yet. And also if I take a look at residuals, a scale residual, I can see the top one is continuity, and continuity is still 10 to minus 2. It should become less than 10 to minus 3. Perhaps I need to wait for 2000 iterations or 3000 iterations to make sure it becomes less than 10 to minus 3. And so for this, I need to make sure all of them become less than 10 to minus 3. And from here, I need to make sure this is completely horizontal. But for the purpose of this tutorial, I think that's very close to convergence. So I'm going to stop it. But as I said, for a practical project, I would suggest waiting at least 1000 iterations or 2000 iterations to make sure it's completely converged and the scale residual, all of them are less than 10 to minus 3. So I press stop, and that's where the problem does not iterate anymore. And I can say the torque was 19 or 1.9 10 to minus 2 or 19.28 10 to minus 3. If I compare with experimental data, this is 23.5 10 to minus 3, and the other one is 19, so 19.3. Because as I said, the geometry of the blade is not exactly the geometry of this blade. I expected to have a little difference between them, but still for a CFD simulation, that's an acceptable error with knowing that the geometry is different. However, I would duplicate that. If I want to do a practical project, I would duplicate that and I would go and create a file in a mesh. How to do that? So if I duplicate that, I can wait and I can use the same geometry, making sure the geometry is the same. I can use the same geometry and I can go to the mesh and I can refine the mesh, for example, 5 million, 10 million. So I can open the mesh and change the mesh, refine the mesh and set up the simulation again and do the simulation and compare my results with the previous one. And also I may try to extend the region. I mean, just having the region bigger, the outer region to be bigger, and in the back especially to make sure that the region is not affecting my simulation. For now, I'm going to show how to see the other results. So for example, you can see the torque here, but also you can see that here in the reports. If I click on reports, then forces, then I can click on moment, then 0, then minus. The axis should be this one. So here the center is, so to see the moment, the center should be 0 and the axis of rotation should be -1, then blades. If I click on print, I can see the moment here. So that is telling me the moment as a result of the pressure is 24, as a result of viscous is minus something. The net total is 19. When so I should compare this number, the total torque or moment, with this number. Sorry, with this number here, peak torque. So that's how I can compare my CFD and validate that. So I had here 19.28, that was 23 or something. So that's something that I have to compare the result. I can also see the force. I might be interested to see the force. So if I take a look at, let's take a look at the geometry again. If I take a look at the blade and the nose, also there's a force on the direction of the flow. If I see, for example, this is the direction of the flow from left to the right in y direction, there is a force trying to push this. This is called drag force. That force is going to push this, and that force is going to be applied to the structure holding this rotor. So that's why this force is important for me. I can see the force. I could have monitored that during my simulation, but I can, after simulation, I can see the force on the nose and blade all together. On the y direction, it is basically on -y. Print, and I can see the total force is 1.33 Newton. That's the force, total force applying on this. In the experimental setup, we cannot see that force, but here in Fluent, we can see that force completely. Also, I'm interested to see, for example, let's make sure the blades are rotating. If I select the velocity of the blade and select the blade here and nose, perhaps, then I can see here, that's the velocity. Always tick this off, so just remove the tick here to see only the velocity on the region that we selected, not on the global range. So the velocity, as you can see, the velocity of the fluid here is higher because here we have a higher speed for the wall, for the blade. That's why the speed of air here is higher. It's a rotational speed. It's as a result of rotation of this blade. And here velocity is 0 because here we don't have rotational speed. Okay, so also we assume that this nose is going to be rotating with the, it might have been fixed, we could have made it fixed, but for this case, we assume that this is going to rotate with the blades. Okay, in practical problem, it might be fixed. We could have made it fixed, but that's how we did this problem. So we assume that this is rotating as well. And here, that's how I can make sure I have defined the rotational axis and rotational point correctly. If the rotational point was here by mistake, then I would have had higher velocity here and lower velocity here. But from these contours, I can make sure the velocity here and here and here are the same. So I exactly define the point correctly, the point of rotation correctly. Then I might be interested to see the velocity field or the streamlines, path lines behind this. So I can click on path line. So let's click on path line. Then if I select blades, then path line. So how many path line? I can skip some of them, 100. So 100 of them I want to skip them because there will be lots of path line starting from the blades. So I will see the path line starting from the blades. If I click on display, I can see the path line. That's kind of a path line behind the blade. If I want to see the blade, I can click on mesh and select the blade and nose and select faces and then apply, then close it, and then I can show the rotational speed here. That's the path line behind the wind turbine, and we can see there is a rotation behind the wind turbine. That's the effect of wind turbine. That's why I would say if I have the domain extend to the back more and more, that would be even better. The reason is because I have some flow rotation and flow field changing on the back. So if I have the back of the domain as far as possible, the result would be more accurate. But I can see here the streamlines behind the wind turbine. Also, I might be interested to see the pressure field on the blades. So if I click on contour, instead of seeing the velocity, I could see the pressure on the blade. So I can see the pressure field. And here the pressure is higher than the other side. So you can see everything here. So pressure is higher, and here is lower because here we have separation sometimes. And we can see other things. Let's see what else we can see. For example, I can create a plane, right click on surface. Let's create a plane so that also I can create a plane in that direction, a YZ plane at that location, create that, and I can show the contour of velocity on that plane. So the contour of velocity on the plane that I just created, plane number 6, and you can see what's going on behind the wind turbine. There's a velocity, and the effect of wind turbine extends to the here, to this point. Perhaps if I have the backside further away, I could have seen more variation here, but because I set this outflow here, that may not be realistic. This might want it to be very back in the realistic problem. So that's why I prefer to have back as far as possible, because behind the wind turbine, lots of things are happening, and that's kind of a wake behind the wind turbine. One thing else that I would like to check, I like check for turbulence. So for turbulence, we are checking always Y plus. What is Y plus? In theory, I will talk about that, but Y plus for this K omega SST on the walls, these two, not global and show on the local range. So Y plus here I can see is 56, the maximum Y plus. If this is above 300, that's a problem. I shouldn't have Y100 above 300. The Y plus, the desirable range is just between 5 to 30. So 30 would be good. 300, above 300 would be somehow above that. That means the mesh is not very good near to the walls. So I have to refine the mesh. But 56 is okay. It's not bad, it's not perfect, but it's okay. So I can say I can rely on the results based on my turbulence model. I will talk about that in theory, and we will see. The other things are velocity, pressure, and I might be interested to see the pressure also in the plane as well. Over the plane I define here. So I saw the velocity and I can see the pressure here. So the pressure on front of the rotor is not that much changing. It's just the normal pressure. The pressure is atmosphere pressure, but back here, because of the wake behind the wind turbine, I'm going to have some pressure, wakes here. That's as a result of wakes. Okay, so that is the end of this tutorial, and I hope you have learned how to model a wind turbine rotor and how to use multi-reference frame to model that.